Now we look at some asymptotic bounds for some common functions. So first of all, the exponential function. So for any exponential function with a base that's greater than 1, it grows faster than any polynomial function. It's a very important relation that we need to basically memorize. So we want to avoid exponential functions, and we would rather to keep a polynomial function, even if the order of that polynomial function is pretty big, but it's always better than an exponential function. We can use the small o notation to indicate this relationship. So the exponential function here, a to the power of n, is a very loose upper bound to the polynomial function. Okay, if the base is greater than 1. So that means the exponential function grows really quick as long if the n turns out very big, as the n approaching big. So in the language of limits, if we place the polynomial term in the numerator and the exponential term in the denominator, so the n, when the n approaches infinity, no matter how big b is and how small a is, as long as a is greater than 1, this ratio will eventually approach 0. Okay, and based on this relationship, we can have an inference that for any positive polynomial function, it grows faster than any, we have a new term, polylogarithmic function. So this polylogarithmic function means that it's the logarithm function raised to the power of some constant k. So that's the polylogarithmic function. And basically, the polynomial function always grows faster than the polylogarithmic function. So that tells us that we want to see the logarithm terms in the algorithm running in the running time of the algorithm. Logarithm is always better than the polynomial running time. So how do we have this conclusion? We can simply replace the logarithm term, the logarithm of n for n, and replace 2 to the power a for a into equation 1. Okay, that will give us, okay, the logarithm of n raised to the power of b, right? That's the polylogarithmic term. And the 2 to the power of a raised to the power of logarithm of n will eliminate the 2 and the logarithm term here, which gives us n to the power of a. So it becomes a clear that the ratio of the the polylogarithmic term over a polynomial function will approach 0 if n is great. So our conclusion is proved. Okay, so that indicates the small o notation here. So I use small o here because it's a more strictly defined notation, but always we can replace it with a big O. Okay, so the big O is a weaker condition than small o, and the small o usually indicates that the big O is also valid. Okay, so let's continue on other examples. So factorials. This is a function that we will see later and in later chapters. It means that it is a given number n, the factorial of n is n times n minus 1 times n minus 2 until 1. Okay, so it has a loose upper bound. So this function is grows slower than n to the power of n, but keep in mind that factorial is a very fast function. Even though it's, so that n to the power of n is insanely fast, and n to the power, and the factorial of n is has a loose upper bound than this one, but itself, factorial function itself is also a very growing fast function. So when we try to analyze the lower bound of factorial function, we can use something called Stirling's approximation. Use this approximation to analyze the running time, the lower bound of it. So we can prove that the exponential function is a loose lower bound of n squared, and a factorial of n. So factorial of n is itself also an insanely fast function. It's even faster than, grows even faster than an exponential function. Okay. But good news that if we take logarithm of n factorial of n, we will have big theta of n times n squared. Okay. So these are useful to memorize, but we don't need to know how exactly the relationship are proved. But it's important for us to memorize that because we want to do our best to avoid the factorials. We want to avoid exponential, and polynomial is somewhat acceptable, but we'd better see some logarithm terms of the running time equations. Okay, so that's some common asymptotic bounds for some common functions. So as a recap for this chapter, we would like to see that we would like to use the intuitive plots here to memorize the big theta, the big O, and the big omega notations. And I think the best way to memorize is to use these three curves. So there's always a threshold you want to satisfy, right? We want to use the threshold n0. That's something we want to choose. And f function, if it's sandwiched by two functions, by two constants, C1, C2, then it's big theta. If there's only just one upper bound, then it's big O. If there's just a lower bound, then it's big omega. That's the quickest way to memorize.